What we've learned so far is that we have this formal hypothesis that is going to posit that alpha 1 is bigger than 0. Okay, that's our a priori belief. The null hypothesis is going to be the opposite of that. And we're going to set up a distribution of alpha 1 hat values, okay, that would derive from repeated sampling and repeated estimation of our equation, okay? And we're going to center that on a value that is assuming that HO is true, okay? And we're going to choose the probability that alpha 1 hat is bigger than alpha critical given HO true. Okay, and we're going to set that equal to whatever number we are going to find acceptable. So if we want to apply a more rigorous test vis-a-vis the type 1 error, we'll set a smaller number. It might be 0.01. If we want to be a little more lenient in our test, we might pick a little bit bigger number like 0.05. But the bottom line is we first pick the probability of a type 1 error and then we use that to infer or choose the appropriate critical value that will give us that particular probability of a type 1 error. Okay? That's the situation that we've got going so far. I want to show you what would happen if we had a hypothesis that said alpha 1 equals 0. The opposite of that would be alpha 1 not equal to 0. Okay? So if we set up our distribution, 0 is the number that would be consistent with the null hypothesis. So we're going to assume that the null is true. And I want you to think about where the rejection region is. That is to say, what values of alpha 1 hat would lead us to reject the null. Well, I think you would say probably that you would reject this null hypothesis if your alpha 1 hat was sufficiently large or if it was sufficiently small, right? So you probably are going to have, or you will have actually, rejection regions in the two tails of the distribution, meaning if you draw an alpha hat from here, you're going to reject that null in favor of the alternative. If you draw an alpha hat way down here, you're going to reject that null in favor of the alternative. Okay? So, not surprisingly, this is called a one-tail test, and a one-tail test will be what you are conducting anytime you have an inequality in your hypothesis. If you have, that is to say, I should say a greater than or a less than sign. If you have an equals versus not equals kind of situation, you're going to be conducting what we call a two-tail test. And it's two-tail because the rejection region falls in both tails. So if we want to choose appropriate critical values for this test, how would that work conceptually? Well, we still want to pick the probability of a type 1 error. But, for example, if we want the probability of a type 1 error to equal 0.05, like it did in the last particular example, we would have to split that between the two tails now. So we would add up this area so that it equaled 0.025, and we would add up this area so that it equaled 0.025, and therefore the probability, the total probability of rejecting the null, that is getting an alpha 1 hat here or an alpha 1 hat here, the total probability of rejecting a null given that the null is true, given that we've centered the distribution on this particular number, okay, would be 0.05. Okay, so we're going to have 0.025 in this part of the distribution, 0.025 in this part, and we will use that 0.025 to find the appropriate critical values here and here, which will divide the acceptance versus the rejection region. So a critical value is just a value that's going to divide the rejection region. Here's our rejection region here from what we might call the acceptance region in here. Okay, so if we draw an estimate in here, we fail to reject the null. It's sufficiently close to 0. If we draw one in here or in here, they're sufficiently far away from 0 that we're going to reject the null in favor of the alternative. Okay, so this is the difference between a one-tail and a two-tail test.